Welcome back, 6th grade students. Today we're taking a look at our Week 12 Bellwork. And again, this is something that's typically assigned in your core classroom on a Monday or Tuesday and due at the end of the week. So be expecting that this is something you'll work on a little bit each day until it's due on typically a Friday. Taking a look here, our first problem says that we're going to use the greater than, less than, or equal to symbols to solve the inequality below. So they're telling us that we're going to do a comparison using these three possibilities. So I'm kind of thinking about these as symbols that I need to apply to this problem. And I gave you a hint here. I said we could use bar models, common denominators, or we could put these in simplest form. And the students that I have worked with most recently really kind of are using that idea of simplifying the fractions using simplest form. So I'll definitely show that. But I'll also show you another strategy with bar models just because I think it makes good sense for students to see this improper fraction, this 14/7, as a bar model. Now, notice that I did call this an improper fraction. It's improper. If you notice, the top number of the numerator is greater than the denominator, so that's how we know that it's an improper fraction, meaning that it's greater than 1 whole. 7/7 is the same as 1 whole, and this is 14/7, so I know it's bigger than 1 whole. So if I were to sketch that out for you real quick, our bar model would have to have sevenths included. And to make 7 equal parts, we would have to make 6 lines. I hope I've done that here. We'll double check. 1, 2, 3, 4, 5, 6, 7. That's good. 7 equal parts, or as close as I could get them in my bar model. Well, if I were to number these off, this would be 1/7, 2/7, 3/7, 4/7, 5/7, 6/7, 7/7. But I need 14 of them, so I'm going to have to make a second bar. And again, I'm going to split it into 7 equal parts, using 6 lines to do that, and I'm going to keep on counting up from 7/7 to 8/7, 9/7, 10/7, 11/7, 12/7, 13/7, 14/7. That's how many they said I had. So taking a look at this bar model, I actually end up with how many whole bars? 2. The entire thing is filled in. I needed all of them. So this 14/7 is really the same as 2, the whole number of 2. I could also look over here at 2/4 and I could try to sketch that out, and I'm going to try to keep it over here so that it's relatively close to the other bar models. I'm going to try to use the same size bar, so I'm really trying to think about the same size candy bar, the same size Snickers, or whatever it is I'm starting with, and I'm trying to make sure that I have the same length to work with. And I want to split this one not into sevenths because my denominator was 7 in the first fraction. It's 4 here in the second fraction. So let's split this into fourths. So using 3 lines to do that, first I split into halves, and then I split those halves again down the middle, so I end up with fourths. Well, how many fourths does it say I have? 2/4. So right here I have 1/4, 2/4. Well, just doing a comparison, if this is the same as 2 wholes, and this fractional bar model represents 2/4, and you might notice that it goes halfway, so it's also equivalent to 1/2. If these were your favorite candy bar, I'm guessing you'd rather have the 2 wholes. I would. If this is a Snickers, hint, hint, wink, wink, Christmas is coming, I would definitely prefer the 2 Snickers over just half of a candy bar. So that means that this 2 whole candy bars is greater than, we use the greater than symbol, 2/4. Or again, 2/4 is the same as 1/2. Now, my students recently have also been working on these improper fractions, and we know how to turn improper fractions into mixed numbers. We take the numerator and divide by the denominator. So when I do that, I say, how many times does 7 go into 14? Well, counting by sevens, 7, 14, it goes in there 2 times. So I'm going to put that 2 here at the back of my quotient, and 2 times 7 is indeed 14. When I subtract, there's nothing remaining. And even if a student decided to write this as a mixed number, they would end up writing 2 and 0/7. Well, that means 2 whole candy bars with 0 pieces left over. And I'm okay with that. That's still 2 whole candy bars, and it's still very comparable. You might also notice that with this 2/4, if we wanted to rewrite that as a mixed number, we could put a whole number of 0 out front and the fraction of 2/4 behind it. I have 0 whole candy bars, but 2/4, just a little tiny part of it. I'd still get the same result. 14/7 is going to be greater than 2/4. Let's go ahead and look at the second problem here, where we get to find the sum of 2 numbers. And if you notice, they're kind of giving me a hint here about what sum means. They may not always do that. They might just give us two numbers and say find the sum. So it's kind of important that you start to recognize some of this terminology. And sum is referring to this idea of addition. I'm looking for the result to an addition problem. Well, let's go ahead and stack these numbers. So I'm going to start with the first number they've given me. And if you remember, addition is actually interchangeable, so I wouldn't have to necessarily put the first number first. Something that I notice about these two numbers is that they have the same number of digits. So I didn't really have to think about placeholders. When I'm adding decimals, that's something we might have to consider. But with these whole numbers, they both have the same number of digits. They both end up going to the 10,000s place. Starting here in the ones place is what we typically do, following the algorithm, the shortcut that we've learned. I have 8 ones plus 0 ones gets me 8 ones. Next I have 4 tens plus 9 tens gets me 9, 10, 11, 12, 13. 13. And when I get 13 tens, I usually keep 3 of those tens and take 10 of those tens to make a group of 100. So I'll regroup here in the hundreds place. Next I have 3 hundreds plus 200 plus an extra 100. So if I put all those hundreds together, I'll end up with 6 hundreds. Next I move to the thousands place, 9 thousands plus 6 thousands. Well, 9 plus 6, that's kind of like, if I took one away from the 6 and added it here, I'd have 10. I'd have 10 plus 5 more. Sorry, dog interference. 10 plus 5 more makes 15, so we'll keep the 5 and regroup the 1. I brought my buddy with me tonight for the video, and unfortunately he's starting to talk. All right, next, I have 7 10,000s plus 6 10,000s plus 1 extra, a group of 10,000. Well, if I combine the 6 and this 1, I realize I'll get 7, and 7 and 7, knowing my doubles, gets me 14. I'm ready to put some notation in here to help me read this number. So because we have these commas and we're talking about the thousands, I'm going to move over here, ones, tens, hundreds, and I'm going to put a comma here between the hundreds and the thousands place to help me read my final answer. And this would read as 145,638. Let's go ahead and try to move on to this next problem. This is something that we're working on currently in our math core class, where we get to talk about finding the product with decimals. So notice this word product. Sometimes they won't tell you what symbol goes with that, and we'll just have to know. But in this case, they give us a hint, product, and they're showing me that it goes with this times symbol. So product is really telling me the result of a multiplication. We give you a hint here. It says, today we can count our decimal hops. Sometimes your teacher calls that the decimal bank. So that's a possibility that you think of it as a decimal bank. Sometimes I call it scoops because we think about ice cream scoops, and that sounds delicious this time of night. So a lot of different options to kind of think about this. The first thing I would tell you to do is let's go ahead and stack them. So step 1, let's stack them. I'm going to take that 37 and 40 hundredths, and I'm going to stack that right on top of the 2 and 1/10. I want you to notice something I very purposely did. I did not line up my decimals. It's not wrong to line up your decimals for multiplication, but it's not necessary. And actually, when we see students line up decimals, it ends up getting them extra lines of work that oftentimes causes errors. So for that reason, I'm purposely going to leave that out. I also want you to notice something else about this first number. Do you see how it has this extra placeholder here? This 0 at the back? Is that something that we could omit if we wanted to? In fact, we could. So this would be another possibility for writing out the problem. I'm not sure if many students thought to do that. But you could have 37 and 4/10 over 2.1, or 2 and 1/10, and you can multiply there. And coincidentally, the decimals do line up, but you'll end up with the same result. Okay? So either way you try this, that should work. Let's go ahead and give that a go with this first problem, the one that I wrote out over here with that 0 the way it was given. First, I would start, and I'd start multiplying like I always do with multi-digit numbers. Using the algorithm, we start in the farthest place value on the right, and we say 1 times 0 is 0. 0 times anything gets me 0. Next, I'd make sure 1 multiplies by the next place value. 1 times 4. Well, that gets me 4. Next, I have one group of 7, and 1 times 7 is 7, and 1 times 3, which is 3. And I know some of you have learned that that's called the Turtlehead Method. Now, I never learned that. I've learned that from my students, and they draw kind of like this idea of a turtle head around here. So there's our turtle. He's facing to the left right now. When you're done doing this first line of work, you might notice that we're all done multiplying 1 times every digit in the first number. So what we will do is we'll move over a place value, and to do that, sometimes your teacher tells you the turtle lays an egg, okay? Or sometimes I say X's and O's, here we go. Or sometimes I say, don't forget Bob. So either way, I need you to remember that we're moving over a place value. We're moving over a unit of 10. So to do that, I need to show that place with an extra 0 at the back. We're next going to multiply going a different direction, and this is where I'm not real clear on the Turtlehead method, if that's something that your teacher calls it. But I will say this, I think you would probably draw another loop kind of like this, like the turtle's facing a different way now. So maybe he's facing towards us, or he's turned a little bit. So we have to take care of this 2 times every number on the top. So we say 2 in this, it's actually in the ones place, but we'll say this 2 is going to multiply times 0, and 2 times 0 is 0. Next we're going to move 2 times 4, and we're going to get 8. And in the next place value we have to get 2 times 7, which gives me 14. And usually we'll keep 4 and regroup that group of 10 to the next place value. And 2 times 3 is 6, plus 1 more makes 7. If you remember, when we're done with these partial products, we get to go ahead and add them up. So I have 0 plus Bob, and I'll get 0. It's kind of a trick question. 4 plus 0, I'll get 4. 8 plus 7, well 7 and 7 is 14, plus 1 more makes 15. Keep the 5, regroup the 1. 4 plus 3 plus 1, well 4 and 3 is 7, plus 1 more makes 8. And next 7 plus nothing, and I could put a placeholder in there if I wanted to. It wouldn't really change the top number, but it would help me see that I have 7 plus 0, which makes 7. Now I have to say there's no way this should be my answer. I just took $37.40 and I almost doubled it. Well, I don't think I'm going to end up with $78,000. I wish I would. In fact, if that happened, I'd totally take my money to the bank and try to double it today. But if you notice, we're looking at decimals, and this is where it says count your decimal hops. So I know in your core classroom right now, your teacher's talking about underlining the decimal places. So behind the decimal in the first number, I have 1, 2 numbers. We put a 2 in what she calls the bank. Okay? In the second number, kind of made a mess out of it here with my Turtlehead method, but I would underline 1 place value. There's 1 number in the decimal. When I total up the decimal bank, I end up with 3, meaning I need to save 3 numbers at the back, 1, 2, 3 places, and then place my decimal. My final answer ends up being 78 and 540 thousandths. This is tenths, hundredths, thousandths. This is one possible answer. Now I do want to point out that if you try it this way, you'll actually get the same result, but if you notice, you're not going to make 3 hops. You're just going to end up making 2 hops or 2 scoops. 1 scoop of chocolate, 1 scoop of vanilla. That still makes 2 scoops of ice cream. Pretty delicious and still an awesome answer. But your answer would look more like, oops, hopefully not with that extra line in there, more like this. You wouldn't have that 0 at the back because we would have omitted this extra placeholder that's not needed there. It still will get us the same result, the same value. It just might look a little different. So again, when we're multiplying by decimals, we ignore the decimal, we stack up the numbers we're given, not necessarily stacking the decimals, and we multiply like we know how to do, and next we move the decimal back in. If you think about why that happens, you're really dividing that top number by 10 twice. When I divide by 10 twice, I'm really dividing by 100, and that next number was divided by 10 1 time. So I want to divide by 10 3 times total. That's really the same as dividing by 10, 100, 1,000. That's why I'm getting to the thousandths place. Just food for thought. Let's go ahead and move to the next problem here, which might be located on the next side. Here's an order of operations problem that I kind of gave you a hint about. I suggested that you think about Pemdas. Now Pemdas isn't a perfect acronym, but it sure is helpful if I want to remember steps in order. So it gives me enough to go on that I usually can get to a really good answer. And it does get a little more complex later on with different types of grouping symbols, but this is a good start for 6th grade. If I look here at the P, it reminds me that I'm looking for anything that looks like parentheses or grouping symbols. The E reminds me to look for anything that has exponents, so maybe a little tiny 2 or 3 as an exponent would be a hint to me, something I might see in a problem right now. Next, the M and the D, they're kind of glued together, aren't they? M stands for the multiplication step and D stands for the division step. And notice that they're close together because we're going to move from left to right in whatever order they're given in the problem. The last two pieces I'm looking for are additions and subtractions, represented by the A and the S. And notice that they're kind of glued together too. They're buddies. They go in order from left to right. So let's go ahead and give this a try. I do know that I've tried this in my classroom the last couple days, and I'm running out of space to show all the work I need to. So I'm going to kind of make a box here and make us a little more room. I think we might need it. All right, first step, are there any parentheses? Oh, I see some. I see some grouping symbols sitting right here and sitting right here. So general rule would be start from left to right and take care of your parentheses. So the first set of parentheses is here with 3 plus 62. So I'm actually going to take care of that addition as my first step. Well, 62 in my head, adding up 3, 63, 64, 65, I'll get 65 as a result. Your core teacher is really good about crossing off the things that you've used, so we get rid of that set of parentheses and bring everything else down. And I have to warn you, I really don't like that multiplication symbol. I try to save the X for algebra. So I'm just going to change mine to an asterisk. The next thing I'm looking for is any more parentheses. I don't want to move away from the P in Pemdas and the P for parentheses before I've taken care of all sets of parentheses if I can. So I do see another set of parentheses happening right here. The next thing we need to do is subtract 17 from 25. Well, to do that, I like to put 17 in my head and count up. 17 and 25 aren't that far away from each other. So 17 in my head and counting up, 18, 19, 20, 21, 22, 23, 24, 25. Just keeping track with some tallies, counting up on the off to the side here. I could have done that with my fingers as well, but harder for you to see. I end up with 8. And I know you can hear my baby in the background. He's crying. He must want to do the math. All right, 25 minus 17 is something that we took care of. We took care of the subtraction, so we're going to bring down everything else we've already used. Oops, so we have a multiplication. We have a 65 out front. At the back, we have plus 3 to the second power. There are no more parentheses, so I could kind of check that off the list. And next I'm going to look for anything that looks like an exponent. Do we have any? In fact, we do. If you look at the back here, we have 3 to the second power. And I want you to be very careful. Do you remember what that means? Well, this big number is called the bass. It's all about the bass. It's the biggest instrument in the orchestra, I bet. And over here we have this exponent, which tells me how many times to use the bass. So it says to write it twice. So I'm going to actually record 3 times 3 to get a final answer. Most popular 6th grade answer is sometimes 6, but unfortunately that's not correct. So we want to try this differently. We want to try to actually multiply. 3 times 3 is 9. And that's what we're going to get from this exponent. We'll cross off then the 3 to the second power that we've used up and bring everything else down. We still have an addition right in front of that. We still have an 8 right in front of that. We still have multiplication right in front of the 8. And we still have 65 in front of all of those. We're ready to look for the next step. Are there any more exponents? There are not. So I'll check that off. And next I can look for M or D, multiplication or division, in order from left to right. So I do see some multiplication happening here. That's the next step that I need to take care of. So I could think of 65 times 8, maybe off to the side. Maybe I need to stack them up and see what I get. If you remember, we've also been doing an area model on this lately, so I could also just kind of give you a quick refresher. 65 is really the same as, oops, that was kind of a silly model, but it wouldn't hurt anything, I guess, to have that line there. Just going to try to make it a little more equal. I'd have 60 plus 5 more, and I'd be multiplying both of those numbers times 8. Well, 8 times 6 is 48, and this extra 0 behind it is going to make it 480. And then 8 times 5 I know is 40. If I were to combine those, I'd get a total area of 520. And you'd also get that if you just like to do multi-digit multiplication with the algorithm up here. Same result, 520 if you tried that. So let's go ahead and record 520 in our order of operations. We'll cross off the multiplication that we used with the 2 numbers that were multiplied and bring down everything else that has not been used. There's one last step here, and I'm guessing you don't need my help to figure out what that is. There is no division, so I can check off these pieces we've taken care of. Look for addition subtraction as a last step, and we do have some. And that's the last thing I want you to do. When you're done, you might want to record your final answer, circle it. And if you notice, we've done a really nice job of making a slice of pizza. This is what I like to call pizza math. That's kind of silly. I don't think you'll ever find that online. It's not a real term. but it kind of makes this slice, this inverted triangle, which is kind of helpful. It tells you that you're organizing your work well. Let's move to the next problem here. I might have to move this box out of the way now. For this next problem, we're looking at a word problem, and I know that sometimes that is kind of frightening in math. Sometimes we see the words and we don't see that words are so much a part of all classes, including math class. And sometimes it's tough to decode these, so we're going to kind of take it easy and tune into some bits and pieces that maybe I've already highlighted, or maybe you spot something else that will be helpful. It says Melissa is making clothes for her dolls. She has 7/8 yards of fabric. Each doll shirt requires 2/7 of a yard of fabric. How many shirts can she make for her dolls? There is this new idea of 3 reads, and in the first couple of reads they actually encourage you to leave out the numbers. So if I were to try that again, it would say Melissa is making clothes for her dolls. She has fabric. Each doll shirt requires a part of that fabric. How many shirts can she make for her dolls? So there's a couple important things jumping out at me. I know I have to start with some fabric, and if you notice here, I've already bolded for you here the starting point. If you're going to make a project, if you're going to sew shirts, whatever you're going to do, it's important to have a lot of material, right? Enough scrap paper, enough construction paper, enough stickers, enough, in this case, fabric. And then we're going to split it into different projects, or in this case, different shirts. So each and every shirt, each one gets 2/7 of a yard of fabric. So in the second read, I kind of go through and I start to kind of decode and figure out what those numbers are telling me. So each shirt is going to get that much. Well, I might be able to make more than one shirt, so I'm really splitting things. When I think about splitting the fabric or splitting the materials or grouping things, I'm really talking about the operation of division. And the last thing that really jumps out at me, I like to code a little bit differently. Oftentimes I will circle. It says how many shirts can she make for her dolls? I know I'm looking for how many shirts, and I'm going to put a question mark right next to those words because that's going to help me do some labeling in a minute. All right, like we said, we have lots of fabric. In fact, we're starting with 7/8 of a yard, and what we're going to do is we're going to split it into groups of 2/7 each time. This wouldn't be a great one to use a model on because I think we'd have to end up finding a common denominator of 56. And I don't think that would be very fun to draw. So I think with this division problem, we might try something that you've learned called multiply by the reciprocal. Now that sounds super fancy. It really sometimes is remembered as KCF. Keep, change, flip. And I know your teacher likes to call it freeze, change, flip. I just get concerned that students sometimes forget which one of these means flip. So KCF tells me to keep, change, flip, or multiply by the reciprocal, fancy words. For the first fraction, I have to keep it the way it looks, so that 7/8 stays the same. Next it says change. So change from division to its opposite or inverse, which is multiplication. And the last thing says flip, which is really where that reciprocal comes in. The reciprocal of 2/7 is 7/2. I'm really ready to go ahead and multiply here and see what we get. So we could check for cross simplifying. 7 and 2, well, they only share a common factor of 1. Actually, both 7 and 2 are prime. And 8 and 7, well, 8's not prime, 7 is, which means only 7 or 1 will go into it. So 7 go into 8? Not so much. So let's just multiply straight across. 7 times 7, maybe using your chart or counting on or skip counting, you'll get 49. 8 times 2 will get us 16. And you might say, hold up, the elephant is smushing the chicken. Okay, that's funny talk for this is an improper fraction. How do you know it's improper? How did I notice that so quickly? And I said, oh dear, poor chicken. I mean, how do we fix this? The top number is too big for the bottom. It means that we have more than 1. So we're going to get some type of a mixed number from this, perhaps. So what I would do is I would treat this like a division sign. This fraction bar always tells me to divide the top by the bottom. Next year, when you move into 7th grade math, you're going to start taking those fractions and dividing the numerators by denominators to get to decimals. So you're going to see more of this. This won't go away. Well, maybe using our chart or counting on by 16s, 16, 32, 48. Oh, that was 3. 3 groups of 16 will go in there. So 3 times 16 is, in fact, 48. When I subtract, there's 1 remaining. No numbers to bring down here. I could put a decimal point, some zeros back there, but I don't really need a decimal to be accurate. I can be exact and precise with long division and a mixed number. So So how many whole groups did we make? 3. How much left over did I have? 1 little piece out of 16. 3 and 1/16. Now, I have to tell you, don't look. Oh my gosh, how embarrassing. Don't look. I'm not kidding, students. Don't look. We would kind of joke that this is an embarrassing answer because they gave me words, I need to give them words back. So what was I measuring? 3 and 1/16 yards? I don't know. 3 and 1/16 dolls? I don't think I want 1/16 of a doll. What are they asking us to find? Going back to that question and the way that I coded it, I circled it, I put a question mark next to it. How many shirts? Could we make 3 and 1/16 of a shirt? Yes, we could. I don't know what that 1/16 will do for us. So someone might argue, I'm just going to write down 3 whole shirts, and you might have 1/16 or enough for 1/16 of a project left. That would be okay also. But for today's purposes, we'll just call this a mixed number, and we'll make sure that we label it, our final answer. The next problem is kind of similar because it says, draw a model to represent the problem, and I said you could check it using KCF, or multiplying by the reciprocal. So the model piece of this could probably be the trickier part. Let's go ahead and try. It says, draw a model of 6/9. So drawing my bar model here, I want 9 equal parts. That means I need 8 lines inside. 1, 2, 3, 4, 5, 6, 7, 8. Those aren't perfect, but they're pretty darn close. I'll call it good. And notice that it says I only have 6 of those 9s. So here I have 1, 2, 3, 4, 5, 6 of those 9s shaded in. They're telling me to split it into thirds instead. So I really want to look at this bar, and I'm going to do a comparison. I'm going to draw a bar exactly the same size, well, as close as I can make it. And this time I'm going to split it into thirds. Well, to go from 9 down to 3, I'm really thinking about 9 divided by 3. For every 3 of these, I can make a line. 1, 2, 3, I can make a line. 1, 2, 3, I'd make it to the end of the bar. And I end up with thirds, 1, 2, 3 equal parts. So they're asking, how many thirds can I make from the 6/9? So I'll kind of extend this line down, and if you notice, I'd be able to make 1 whole group, and bringing these 3 pieces down, they would equal another whole group of 1/3. I'm going to get the answer of 2. I can make 2 whole groups of 1/3 using my model. Now I did say you could check with keep, change, flip, or multiplying by the reciprocal. So let's keep the first fraction. Let's change to multiplication. Let's flip or write the reciprocal, which means that the numerator and the denominator switch places. And when I'm ready, I notice there is some cross simplifying, so maybe you notice that this 3 and 9 will cross simplify. You could divide them both by 3. And if you don't see that, we could just multiply across and then simplify when we're done. So 6 times 3 is actually 6, 12, 18. 9 times 1 is 9. Oh, I know that 18 is 9 doubled. So that 9 actually goes into 18 twice. And I'm only doing that because that numerator is too big. That elephant is smushing the chicken. So I really want to divide the top by the bottom. I might get a mixed number. And 9 goes in there twice, we said. And when you subtract, there's nothing remaining. I could write 2 and 0/9, but that's really the same as 2, isn't it? And look, my answer is the same whether I use the model or the reciprocal. Let's go ahead and move ahead to the last couple problems that we have here. Oh, the last problem, in fact. It tells us to find the quotient. And I'm just guessing because I write nice and big for students that maybe I'm going to run out of space. So I'm going to bring my box back in here and see if that helps us out a little bit. Well, we have taught our students an acronym, something that we found online and we found kind of helpful for kids. Sometimes we help you remember the steps of this by writing, does McDonald's serve cheeseburgers? Does McDonald's serve cheeseburgers? These are the steps we use for division or long division each time. The first letter tells me to divide. The second letter reminds me that I need to multiply. The S tells me to subtract. The C, some students omit this, some teachers omit this, tells me to check something. And my students actually have had a lot of success using this checking method. That's a good way to check and see if something's going right or wrong along the way. And the last step here, the B, is for bring down. All right, Back from another dog run, but we're going to try another long division problem here. So again, just reminding you that we're going to use these steps of dividing, multiplying, subtracting, checking, and then bringing down. So I have a divisor of 25, and gosh, those are tricky when I have two-digit divisors. The good news is this one's kind of nice because it reminds me of money. So if you count by your 25s, you'll probably be in pretty good shape. So I think of 25, 50, 75, 100. So counting by 25s, it's like skip counting or counting my quarters. Next I have $1.25, then $1.50, and $1.75, and then $2 or 200 cents. So kind of using what I know about counting by quarters, this is probably good practice for someone that needs help with their skip counting or thinking about money. This is a pretty good skill to have down. So next I'd have $2.25, $2.25. Another quarter would take it to $2.50, and then $2.75, then $300. If you notice, I very purposely have tried to stack these up so you're starting to see the pattern. 25, 50, 75, 100 happens every time. 25, 50, 75, the next 100. 25, 50, 75, the next 100, and so on. And I could keep on doing that, but I think I've probably gone far enough to make that work. Hi, Grizzly. Okay. Next, we're going to divide here. So we're going to try to use that skip counting to help us. So I start with this divisor and I say, does 25 go nicely into 1? Well, actually, I could divide it for sure, but I'd end up with a fraction or a decimal, and I'm trying to make whole groups. So could I take that 1 and break it into 25 whole groups of something? It'd be kind of difficult to do. I'd end up with, again, smaller pieces. So we would usually say, no, we're not going to do that. We're going to try to get a whole number in each group. So we'll put a 0 up top. So the next I'd move over and I'd say, well, let's trade that 1,000 in for 10 extra hundreds. So I'm going to treat this like 16 hundreds. So if I have 16 of something, could I give you a group of 25? No, looking over here, no. 25 is the first number or first multiple I got, so no, that's not going to work very well, is it? So I'll put another 0 above that 6. Well, next I trade in maybe those 1600s and turn them into 167 groups of 10, 167 tens. If I have 167 of them, could I break them into groups of 25? Or could I make 25 equal groups somehow? I sure could. So I come over here and I look at my skip counting and I try to get as close as I can without going over. I'm looking for 167. I have 125, 150, 175 is too much. 167 is in between these, isn't it? So I'm going to use this 150 to help me. So the question is, how many times was that? Counting by 25s, that was my first, second, third, fourth, fifth, sixth multiple. So I'm going to put a 6 up top in my quotient. And I'm going to say 6 times 25 is 150. That's that multiplication step that we just did. Next, I need to subtract. So subtracting 7, take away 0, I get 7 leftover tens, I get 1 leftover 100, and no leftover thousands. So that we're getting closer to an answer. This is where we could debate about whether or not we want to use this check step or not, and I suggest you do. If you have 17 remaining, you want to make sure that it's smaller than your divisor. Is 17 smaller than 25? If so, things are going well. If not, you want to backtrack and you want to see if you can bump up your quotient a little bit. Take out a few more groups until you don't have a larger number remaining. Well, because things check out for me, I'm able to bring down the next place value. So now I have 170, and I'm going to try to split it into 25 equal groups. I want to see how close I can get. So if I'm looking here at my skip counting, well, 170 is also in between 150 and 175. I'm going to use the same 150 again. So if you remember, that was 25 times 6. So the 6 goes in our quotient, and 6 times 25 got me 150 before. It does again. And when I subtract 0, take away 0, I get 0. 7 take away 5 gets me 2. And some zeros up front if I want to show them. Well, there are no place values to bring down. So I could think about it, finishing my subtraction and just doing one last check before I move on. Is 20 smaller than my divisor of 25? And the answer is yes. So for that reason, I would look for another digit to bring down, but I don't have any. So I'm going to stop there and I'm going to write this as a mixed number. So I'm getting 66 as my whole number, 20 leftover pieces out of the 25 that I was trying to put in each group. This isn't a bad answer. In fact, you might get yourself a smiley face, but there's one more step that I'd love for you to take. If you notice that 20, 25ths, those numbers look like they both share a common factor. We want to see if they can simplify. So is there a number that divides into 20 and 25 nicely? If you're using your multiplication chart, you're going to look across the 2 row and see if you see 20 and 25. No, 20's there, but not 25. Next, you're going to look across your 3 row and see if they're both in the 3 row. Neither one divides by 3. Are they in the 4 row? 20 is, but not 25. And I'm going to look one more row because I see here in the 5 row, 20 and 25 both share a common factor of 5. Let's divide the top and the bottom of our fraction so that we get an equivalent fraction with smaller or simplest form. So I'm going to get 66 as my whole number, still stays the same, but 5 goes into 20 4 times, and 5 goes into 25 5 times. This is in simplest form, and this is the final answer. It will get you a gold star or maybe a red star for tonight. All right, hopefully this was helpful for those of you who asked for this video. Sorry about the dog interference, but hopefully you got some practice with our decimals, some more whole number operations, and even a word problem hiding in there tonight.